So in the next chapter, quite naturally, we will talk about the derivatives of trigonometric functions. We will actually this semester skip the inverse trig functions and their derivatives. Instead, we're going to do quite a few applications of the trigonometric functions and how their derivatives can tell us more information about them. So first of all, let's think about how we would construct a derivative graph from that of a sine or cosine function. So first of all, this is my, let's say, sine of theta. What do we have as its derivative? Well, remember that if I want to draw the derivative graph, I have to think of the slopes of tangent lines of the original function and then graph the actual slope on the derivative graph. So for example, there are certain points where the slopes are easy to see. At pi over 2, I can see that the tangent line is going to be horizontal, which means that on the derivative graph, that will represent the slope of 0. So I have a point right here. Next time there's a horizontal tangent line is at 3 pi over 2, which means that 3 pi over 2, I'm also going to have slope of 0, and so on. Just like the sine function has this period, that means that the horizontal tangent lines will also appear periodically. Now, what is happening between, let's say, this point at 0 and this point at the slope 0? Well, I can see that at 0 the slope is actually fairly steep. In fact, it's the steepest it's ever going to be on the function, and then it gets less and less steep as we get to the flat point. I'm going to eyeball this as a slope of 1, so I notice that it's getting less and less steep as it approaches the actual slope of 0. What happens then is the slope becomes negative. At first it's just slightly negative, and then it becomes more and more negative until it's the steepest negative at pi. So I am going to approximate that this is going to be at -1, and then following similar logic, I will see that my function will curl back up and move around. What I notice, of course, too, is because the sine is the periodic function, the derivative of it will also repeat itself with the same type of period. So I know that I can repeat this pattern on both sides of my function. I also, even though it's a pretty rough sketch, immediately recognize this graph as actually the graph of cosine, which gives me some idea of the fact that the derivative of the sine function is actually a cosine function. So if I label this y, then this is going to be y prime. Now, this is by no means an actual rigorous derivation of the fact that the derivative of sine is cosine. In order to derive this properly, I would have to pull out the definition of the derivative, so the limit as h goes to 0 of sine of theta plus h minus sine of theta all over h, and then do a bunch of various trigonometric simplifications on that quotient. I'm not that interested in that level of rigor. I am more interested in really internalizing the fact that, at least justifiable from the graph, these two functions are connected to each other via the derivatives. If I start with the cosine as the graph, then following similar logic, I can produce the graph of its derivative. And I encourage you to actually go through this process to notice that the graph you're going to get is going to look something like this. And again, because it's a trigonometric function to begin with, the derivative of it will also repeat. And what we can notice is that the derivative in this case is negative sine of theta. So let's say we record what we have so far. The derivative of sine of, let's start using x, is going to be cosine of x. The derivative of cosine of x, we've just at least somewhat justified visually, is negative sine of x. And if we take these two things to be true, we can figure everything else out about other trigonometric functions using their relationships to sine and cosine. For example, if I would like to compute the derivative of tangent, I can first of all recall that tangent is actually sine of x over cosine of x. And that I can take a derivative of using the quotient rule and the derivatives of the sine and cosine that I have just come up with. Let's see how this would work out. So the quotient rule says, first of all, the derivative of the top which is the derivative of sine, which will be cosine, times the bottom, so times cosine, minus the top, so sine of x, times the derivative of the bottom. So the derivative of cosine of x is minus sine of x. So times negative sine of x, I will turn this into a plus right away so that I don't have to rewrite this entire expression. And then the quotient rule says to divide by the denominator squared. Excellent. Let's see what we have on top here. I have cosine squared plus sine squared. Well, I know that cosine squared plus sine squared is just 1 due to the basic trigonometric identity, which means that what I have altogether here is this expression is equal to 1 over cosine of x squared, or I know that 1 over cosine of x is actually secant, and because the cosine here is squared, I'm going to have secant squared x. This is then the derivative of tangent. The derivative of tangent is secant squared x. You can similarly derive the derivative of actually secant function to see that the derivative of secant will be, after some number of steps, after writing down that secant is 1 over cosine and whatnot, you're going to get secant x times tangent of x. Okay, these are the main 4 trigonometric functions we're going to work with. The formulas for cotangent and cosecant are actually symmetric to these two and can be derived similarly, and you can always look them up to actually use them. Let's now try to see how these new derivatives work together with other differentiation rules that we have seen before, such as constant multiple rule, addition and subtraction rules, chain rule, and whatnot. So my first function here, I have a of x is equal to 4 sine x. So remember that constant multiple rule means that I can leave the constant alone and then take the derivative of the function itself. So the derivative of sine of x is just cosine. So overall, I'm going to have that the derivative is 4 cosine x. The next function here, I have tangent of 7x. Now I can see that this 7x occurs on the inside, which means that this is my inside function and tangent is my outside function. So as per the chain rule, I have to first take the derivative of the outside. So I first have to take the derivative of the tangent as a function. The derivative of tangent as a function is secant squared. And remember, according to the chain rule, when I take the derivative of the outside, I keep the inside as is. So first of all, I'm going to have secant squared, but with the same inside of 7x, times the derivative of the inside. So the derivative of 7x, which is just 7. Okay, I can of course rewrite this to be a little more familiar with the constant in the front, but this is just fine as is. For this next one here, I have sine cubed of x. Now, this notation sometimes gets a little confusing because of where we place the power on the trig functions. So for the first few examples, I recommend rewriting it so that the power is visibly the power of the entire sine of x, because this makes it clear that now my inside function is the sine and my outside function is the power, which will then dictate the order with which I'm going to compute derivatives using the chain rule. The chain rule claims that first we actually take the derivative of the outside. The outside is the power of 3, which means this will come down to the front and the power will get reduced by 1. So 3 sine squared x times the derivative of the inside. So the derivative of sine of x, which is, as above, actually equal to cosine of x. Excellent. These are just the first few examples, and I strongly recommend that you practice a few more just to get comfortable with how to utilize other differentiation rules with the trigonometric functions. Let's take a look at an application. I've already mentioned last time that a lot of natural processes are cyclic, for example, on 24-hour period or the lunar cycle or the annual cycle. One of the easiest ones to track are heights of tides, and in fact, many places do track that because it's important for a variety of reasons. We have lots of data, and so I just pulled up data from the place named Tom's Cove in Virginia, if we just take a look at what the tides look like in that place, we can see that this is very clearly sinusoidal. This is one of the reasons I picked this place. The patterns here are just so symmetric and so perfectly sinusoidal that it's easy to actually model this function. So I took some of the data points and I came up by hand with a function that represents the tide heights of this place fairly closely. This is the function that models that. Once we have the function, we can predict a number of things and we can ask a number of things. For example, according to my function and according to the data, when is the tide highest and when is it the lowest? When is the tide coming in and when is the tide going out? What does it mean to take the derivative of it? What information would that provide? So let's take a look at how we can use our knowledge of trigonometric functions to actually analyze the heights of tide from the given model. First of all, the first question asks, when is the tide highest and lowest? This seems like it has a lot of information in it, so you sort of have to zoom out a little bit to notice one very important thing. This cosine is just one big chunk of this entire function. So if I were to describe this function to somebody in fewer words than written here, I would say it's 1.8 times a cosine of something plus 2.2. So immediately I know, for example, that cosine is bounded between -1 and 1, and that is something I can definitely use to my advantage. When is the tide the highest? Well, the tide is the highest when this quantity here is the biggest it can be. Now, no matter what is inside of cosine, I know that the cosine itself can never be bigger than 1. The maximum value of cosine is, in fact, 1. Now, I have to think about when does that actually happen. Now, I'm going to do that in conjunction of analyzing when is the tide the lowest. So first of all, I have to then think about when is cosine value the smallest, remembering that it can in fact be negative, right? So 0 is not the smallest that cosine can be. -1 is the smallest that it can be. So a minimum value of cosine is -1. Once I know that, all I have to do is figure out when does that happen. First, I can do something a little bit simpler and figure out what it is when it does happen. So the highest actual tide is what? Well, when cosine is 1, I'm going to have 1.8 times 1 plus 2.2. So I'm going to have altogether 4 feet. And the lowest tide is when the cosine is -1. So I'm going to have 1.8 times -1. So minus 1.8 plus 2.2 or 0.4 feet. This is also useful information to have, for example, if you're building a pier or want access to the water's depth at any point in time. Now let's think about when does that actually happen. What is the definition of cosine? Remember from the unit circle, cosine is the x-coordinate of the point on the unit circle. So if I drew a little unit circle on the side here we go, I can see that the highest that the cosine is, the highest x-coordinate is this point right here. Whereas the lowest that it can ever be is going to be at this point right here. This is the value of 1, which will produce the highest tide. This is the value of -1, which will produce the lowest tide. Okay, and now all I have to do is then figure out when does my angle equal either of these two. Once I have stripped away the fact that cosine is the x-coordinate, all I have to work with is its actual inside. So maximum value at angle 0, minimum value at angle pi. So what am I going to have? My angle on the inside then for the maximum value has to equal to 0. So I can set pi over 6 t minus 11 to be 0 and then solve for that. Now this is not going to be too difficult. I can see that t is in fact 11 and t is hours after midnight, so I know that this is 11 a.m. For the second part, I need the angle to be pi, so I'm going to set whatever is inside the cosine to be, in fact, pi. So all together, then I have this expression, and if I solve it, I will get that t is equal to 17, which in hours after midnight means 5 p.m. Now, one thing you have to be careful about, and I'm going to leave it for you to ponder, is, are there others? One thing that is difficult and you have to be careful about with trigonometric functions is the fact that they are cyclic. So just because the angle happens to be at these 2 points doesn't mean that these are the only options for those angles. If I go for another roundabout, I will hit the same angles, but with a different measure. So I will hit the 0, I will hit this point again, but not at angle 0, but rather at angle 2 pi. I will hit this point again, but not at angle pi, rather at angle 3 pi. So think about how will we compute these various other occurrences of the needed angle and how many of them I have to actually take care of. Okay, think about that. This is a little bit of the homework for you. Let's take a look at the second part of this question here. Find and interpret h prime of t. Okay, so what we have to do, first of all, is take the derivative of this expression. What are we going to have here? Once again, it's probably best to zoom out and think of that as just the cosine value. So altogether, first of all, what I have is the constant that I'm going to leave as is, 1.8, and then I have the derivative of this giant cosine. The derivative of cosine, which is the outside function here, is negative sine. So I'm going to pop a negative up front, and I'm going to have a sine. I'm going to keep the inside as is, and then multiply by the derivative of the inside. This is my inside, so I need to multiply by the derivative of it. This is also not too hard. Remember that t is our actual variable, so this number is a constant times the variable, and this 11 is actually just a constant. So overall, the derivative of the inside is going to be just pi over 6. What are the units and what is the meaning of this actual expression? Well, the units for the derivative, if we would like to write it in the other format, is dh by dt, and then we can read off the units as whatever the units of height is divided by the units of time. So this will be feet per hour. And of course, the meaning of that is this is the rate of change of tide height at time t. Now, there are a number of other questions that one can ask, and in particular, one question that is connected to the first one here is, if we know when the tide is the highest and the lowest, what about when does it come in and when does it actually come out? This is the third part of this question here. What we can do is think through how we've obtained these points and what does that mean for the movement between highest and lowest, or we can also take a look at the graph of this function here. This is the graph of this function that I've actually come up with an expression for as the model for the corresponding data that I've collected. If this is the graph of my function, let me first of all label this through. So we said that time was in hours after midnight, which means, for example, that right here, this is 5 hours after midnight, this is 5 a.m. This highest point up here is at 11 hours after midnight, so 11 a.m. This point I can see at 17, which means 5 p.m., and this point up here is going to be at 2300 or 11 p.m. So this already justifies why you should be looking for more points here to answer the question, when is the tide the highest and when is it the lowest? So this is a little hint to your previous homework exercise here. But from the graph and from just thinking about what happens between local, or in this case global, maximum and minimum of a continuous trigonometric function, I can see that the tide is coming in between 5 a.m. and 11 a.m. because that's when the height is increasing. It's also coming in between 5 p.m. and 11 p.m. What do those time intervals mean in terms of the derivative? So for both of these regions, what is it that I can say about the derivative? If the tide is coming in, it means that the rate of change of height of the actual tide is positive, which means, of course, that the derivative on these regions at any point between 5 a.m. and 11 a.m. and 5 p.m. and 11 p.m. is in fact going to be positive. Now, of course, the question can be phrased in the opposite direction. For what hours is the tide going out? And that will give us the other time periods. I mean, on the graph here, the one I can see fully is between 11 a.m. and 5 p.m. Of course, that means that the height of tide is decreasing, which means that the derivative on this region is going to be negative.